2.6, we're doing rational functions. Rational functions. Rational functions. Rational functions.
They need to be quiet.
Yeah, rational functions.
Find the domain.
The better the moron functions.
So,
Right up your alley, man.
Oh.
anyways, rational functions and their graphs. So a couple things that we're going to do with that. We're going to find their domains of relationships. Use the arrow notation. Arrow notation is just ridiculous. Guess that passes. We're going to look for some asymptotes, vertical and horizontal, and maybe some oblique if I think that's in there, it might not. Transformations, graphing them. Yeah, side asymptotes. And then solve applied problems. I don't know if we'll get through this whole thing. If we don't, that's okay. Please make sure that you understand before we move on to the next topics because this is going to be big. Thank you. So, can I change this slide?
Yeah.
I don't like that I can't see if this is working or not.
What the? Really warm. I'm like really warm right now.
Can I change the slide? Torres, you still writing? You sure? All right, cool. Let's get to it. Nothing to it but to do it. So rational functions, of course, are when you have like a fraction and you got the numerator is a polynomial and the denominator is some type of polynomial. Rational functions, right? Don't really have to say much about that. Now you want to be very careful as far as domain is concerned because the problem with having a rational expression or rational function is that the denominator cannot be 0, right? We break math when we have a denominator of 0, right? So that's really what we're after. We cannot let that denominator be a 0. Questions on that? That's probably going to be our biggest challenge when we're trying to do these, always. Okay? Can I change the slide? Yes? All right, cool. So let's take a look at this problem for this domain. Now, obviously, we already said the denominator can't be 0, right? So we're going to say that x cannot be 5. Okay? What's going to happen there is that we're going to have discontinuity. I think we talked about that in Algebra 2. You should have talked about that in Algebra 2. We'll have discontinuity there. And then there's two types of them, correct? There's the removable and then the non-removable. Okay? In this case, because we can factor the top to x plus 5, x minus 5, that discontinuity is removable, which means that instead of having an asymptote over at 5, instead of saying you can't be there at all, okay, what will happen is the function will go through there, but it'll have an open circle over at 5. Now when you graph these, your 84 doesn't have that much detail. You won't be able to see that gap in there, but you should know that it's there. It'll just make it smooth continuous. You won't see anything different, but you need to know that that is going to be there. So as far as this is concerned, domain, x can be any number except for, let's see here, we can write this a couple ways. We can say, what is it? We can go negative infinity to 5 to positive infinity, if that's interval notation. We can say x is an element of all reals, except x cannot equal 5. I don't know, whatever other notations you can think of. All we're trying to convey with the domain is what x can be, and at the same time what it cannot be. Okay?
Do you want to change it yet? Please.
Oh, for sure. I just have a swig of my water. My hydrogen oxygen cocktail. I really enjoy that 2-to-1 mix. Water.
Okay, you're good.
We're good?
I left my water at home.
Greg, can you close that and take your earbuds out, please? Take these notes. Thank you. All right. Please find me the domain of this bad boy. Joseph, thanks for closing your laptop, taking these notes.
I missed the time when Oop put the Roblox thing.
Huh?
It was a Roblox thing.
Only the
Huh?
Roblox understand.
I understand.
I don't,
It's
I'm
easy.
actually.
It's where it started.
I know.
Man, you guys don't know the internet I used to know.
Sorry, it's
Yes, I
different
do.
than what it used to be.
I
I
really
was
don't.
born in the 2000s.
I don't think you have to call the internet.
I was born
But it-
in 2000, close to 1999. But what year were you?
You know, I was born in 2002.
I was born in 2006.
Alright, question goes to.
I mean,
Hey, where did my dojo go?
we won the what? Think back to that before you were December 30th.
Yeah, that and cash money.
Cash money. Young money.
Gunnar Gary, thank you for participating. What did you get for a domain, please? Well, it could be something. So you got. You have this?
Yeah.
So let's talk about that, okay? What's up? Why should it have two domain restrictions? So we have to stop and think about this. You guys remember the zero product rule that we used to use, where we had x plus 5. Let's do it like this. Oops, sorry, didn't mean to do that. X minus 5 is equal to 0.
Oh yeah, and then you figure out your two x's, right?
Well, here's what we're asking math to tell me when we do this. When do these guys make 0? So if we stop and we think about this for a second, in order for this to be true, either this guy right here is a 0, or this guy over here is 0, correct? Now, regardless of that, I don't want either one of them to be 0 in the case of my rational expression, right? So if I looked at this piece, what can x not be in that piece? It can't be negative 5, right? Because if it was a negative 5, then negative 5 plus 5 would make 0, and 0 times whatever number is still 0.
Yeah.
So based on the first binomial, x cannot be a negative 5. Now taking that same idea and applying it to the second binomial, then x cannot be positive 5. So if you want to write this as a domain, I would just go with the easy. X is an element of all reals except x cannot equal. Oh, let's do something fancy here. Plus minus 5.
Ooh.
The other one.
What?
The
The interval?
yeah.
If you wanted to do it at interval, you would say negative infinity all the way to negative 5, union, negative 5 to positive 5, union, 5 to positive infinity. Okay?
Yeah, I hated unions and
Oh my god.
I finally understand. You know, we didn't learn that last year. We didn't learn unions.
Well, I'm glad you're getting it. Very important.
We learned how to use what a union.
Huh?
I had to, I'm sorry.
Questions on find the domain?
Nope.
Cool, I can do that.
Is that like your favorite song?
Yeah. Not my favorite. It's my favorite melody. It's always in my head.
Okay, what's your favorite song?
My favorite song is
Like
Billie Jean
me.
from Michael Jackson.
What's that?
Yeah, Michael Jackson, love him.
Why is there there?
So that's your favorite song? Is that your favorite song from him?
Billie Jean?
Yeah. I always liked Smooth Criminal.
I like it. Really cool.
I've always loved Thriller.
It was alright. It's not as good as
That one. That's my favorite song. I just really like it. I mean, I like Mr. Burke, but I like it.
Okay.
Yeah.
I can wait.
Are those for me?
No. Hey, I have a toaster back there if you want to toast them.
What the? Yo, honestly,
It's an oven toaster, but it should be open. Right behind Greg Hollywood. Oh yeah.
When you just have to come in here for lunch. Hey, can I put my noodles in here? Yeah.
I can change it now?
Yes.
Okie dokie. Okie dokie. Now, take a look at this. Thank you. Find me the domain of this guy.
I did.
Already did.
What is it?
Just kidding.
Hold on. Hold on.
This is a good one.
Oh my goodness, wait.
I like this one a lot.
Wait, hold on. Oh, wait a second. Yeah, well, because x minus 25 is x minus 5 times x minus 5.
See with the Roman numerals?
No Roman numerals?
Oh, I know. Is it gonna be 5 on? But it can't be on.
Is it all reals? I was right.
I knew it.
Take that.
It's all reals.
Wait, how?
Okay. So, my only problem is that the denominator is a 0, correct? So, if I did do this, this is kind of nice because I can throw that.
What the hell did you do?
Did I do anything?
Yes. Yes, you did. So, I'm going to ask math. Hey, math, when does x plus 25 equal 0? Because I wants to know.
It's gonna be
That means that x squared is equal to negative 25. Once I do that, I'm going to get 5
5.
plus or minus 5i. Would I ever pick a real number?
Like, not the biggie.
Could I ever pick any real number that would break that then? What
No.
would I have to pick to break it? Some imaginary values.
No.
Okay? You can also think about it this way. You can just reason your way. What number could I pick to plug in here? Well, positives are okay, right? But if I plugged in some negatives, would that be a problem? No, because a negative times a negative makes a positive again. So this one is just fine. Questions there? All right, moving on up. Here is, why is there an X here? Oh, is this what I was trying to write in?
Yeah.
I'm sorry, it's just arrow notation is just funny to me. It's called arrow notation. This first one, I don't know if you can see it very well, says X approaching A from the positive side. So that's what that arrow really means. It's approaching. So if you're approaching from the positive side, that means if you're doing this, you're approaching some place from this area. Does that make sense?
Yeah.
I'm coming from the positives.
To the negative.
The other one says approaching from the negatives. That means I'm coming from this way.
Oh.
Okay? Now, do you guys remember that Mean Girls expression? The limit does not exist? This is the beginning of that. This is the beginnings of what that would be doing. Notice how my two arrows are approaching some specific point, right? Some point that lives right here. Did you ever see that? My little two arrows, I kind of did that on purpose.
Yeah.
That would be the limit. That red point would be the limit. That's what my function is, approaching from both sides. And that would be the limit. Now, if my arrow was pointing here and the other one was pointing somewhere else, then guess what? They're not pointing to the same thing, are they?
No.
The limit does not exist. Huh? When would you over what? In calculus. Because in calculus you'll be looking for a limit.
Never.
Yeah, actually, there are. I'd have to go back and think of all the problems because that's where you do a lot. You take a lot in calc, you learn some stuff, and then you apply it to real stuff. With calculus, it's very different because there are like two big ideas behind it. I think I talked about them, right? One was like in regular algebra, we always look at the average rate of change,
Yeah.
but in calculus, they look at instantaneous rate of change. Okay? So, like they'll do some weird things, like they'll take a cone, because farmers use cones for putting water in there, right? And like they'll say, okay, there's this cone-shaped tanker full with water and it's pouring out at the bottom at a certain rate, obviously, can you see how it would be different? Like it would go slow at first, but then it would speed up. They'll ask you questions like that, so they're looking at some limit that it's approaching. You guys see the other two? You guys okay with those? Draw the graphs?
Yeah, like where the arrow.
What do you mean?
It's like from the origin.
So for like,
Like for the X, just A, right?
x approaching a from the positive side? You want a graph for that?
They want a graph for all of them.
And the negative, like the infinity one. But how do you figure that out? What would it look
Well, you'll have a graph already, right? And then they're gonna say, hey, where's the function? What's it approaching from the positive side at some point? And you just figure out a point. All you're really learning right now is that this is saying approaches, is looking at, or moving towards. We'll talk about what that means in context in a little bit. So to draw your picture is kind of weird. It's just you're coming in from this side, you're coming in from that side, right?
How does it supposed to be? Is that the one where the limit designs is?
Yeah, that means it goes on forever. Yeah, so if you think about,
How do you know if it's coming in from negative infinity or positive infinity? It never ends.
well, positive infinity is on this side, right?
Yeah.
And negative infinity is on this side,
What is it
and negative infinity is on this side, and positive infinity is over here as well.
So it just goes.
So if I had an asymptote, and I think you guys have seen these, right?
Yeah.
And maybe we'll throw in a graph that looks like this. Oh, I missed it. Totally missed it. Like that. And then the other part would be like this, right?
Yeah.
Well, if I'm looking from the positive side, what am I approaching?
A positive.
I'm headed up towards positive infinity, aren't I?
Yeah.
Okay. But if I'm coming over here from the negative side, I'm headed down towards
Negative infinity.
negative infinity.
Oh, so. Okay.
It's not like gotcha notation. It's just like, where are you going?
Yeah.
We're going here.
Where is you?
Where is you? You are here. Like this. See that?
Oh, yeah.
Definition of a vertical asymptote. So a vertical asymptote is just an imaginary line. It's not really there. We draw them because we kind of like to visualize things. So what you're looking at here, here's A, right? Asymptote. Here's asymptote A. Those are imaginary lines that just our graph will get closer to, but it will never cross it. Okay? It will get infinitesimally close, but it will never touch it. And that's mind-blowing to me. It's like, that's just mind-blowing. You guys okay with this? Does that make sense now? All of it together, all four of those interpretations? I can change the slide then? Same idea. So locating vertical asymptotes. Where will you find vertical asymptotes? And I think we talked about that, right? Can somebody repeat it just for the sake of it? It's going to be at the zeros of the denominator.
I thought it was just
At the zeros of the denominator. Whenever that denominator becomes zero, you're going to get vertical asymptotes. So like when we did here, I should get vertical asymptotes over at 5 and at negative 5. ¿Preguntas? Vertical asymptotes will be found at the zeros of the denominator. Okay? I can change this? Okay, will this have vertical asymptotes? You guys see our function up there? Whoa, wait a minute, that was different from mine. Did I skip a slide? I think I missed a slide. I wanted this one to be, let's add one then. So if I had x over x squared minus 1, where would I have asymptotes at?
Or positive and negative one.
Alright.
Oh, so if it's like.
What does x squared minus 1 equal 0? X squared equals 1. Take the square root. Because I took the square root of a square, I should get plus minus 1. No. So, yeah, that's trippy, huh? Graphs will get close forever, but it'll never touch it. And then you might get something like this, and then you'll get something like this. Sometimes. Before we used to refer to them as restrictions because you couldn't be that, for the reason that that's what they are. So yes. He will never be there, so it'll be an asymptote, yeah. Miss what? He didn't miss me that much, he didn't stop saying hello.
Yes, he said love you. Yeah, he said love you.
But you were talking.
Tell her I'm sorry. Tell her I miss him.
I don't think he's gonna forgive me.
He'll forgive me. Okay, what's up?
Really good.
Oh, I'm good.
Don't deny it. Smells really good.
Now that I smell it, it does like.
That smells better than your sandwich.
It really
Like, just like.
Oh. Thank you. All right.
I don't have money for snacks.
Someone that's
You.
full of themselves.
What?
Someone who's full of themselves.
My mom called me a narcissist. I'm like, Mom, that's too big for a word. Don't speak to me in that language.
You know what? I'm recording, but you know what? I think that everybody in high school is a narcissist. Everyone is just in love with themselves.
I love myself.
That's the opposite.
I hate myself.
I'm
I don't care what anyone is like.
Why?
Ooh, maybe?
I don't know why. I think we're just at that age.
Yeah.
It's like we have to.
Thank you. Moving on.
Yeah.
Thank you. Moving on. Notice how this rational function has a denominator of x squared plus 1, which means that you can't have any asymptotes, right? So there are none in the graph.
Wait.
Wow. Moving on.
No, but so
Question.
when you have a positive, when it's x squared plus whatever, you can't have an asymptote, right?
Not necessarily, because what you'll have is imaginary values that would break that technically, but there's nothing to put. You wouldn't put imaginaries in there.
Yeah.
Okay. Now,
Okay.
horizontal asymptotes. Horizontal asymptotes.
Isn't that when you make all x's?
Here's your definition of a horizontal asymptote. The line y equals b is a horizontal asymptote of the graph of a function if f of x approaches b as s increases or decreases without bound. That just means you're going to get closer as well. It's just like a vertical asymptote, except they are horizontal. They're horizontal. Okay? Yeah. And there's going to be a couple rules for these.
Remember the numerator?
I was able to heal myself already.
Wait, that would be confusing.
When you're supposed to
Where are
like,
horizontal asymptotes found in the equation?
I'm going to show you right now.
yeah, I was just about to ask.
There's going to be 3 rules you need to know. Okay? And here they are.
What the about Jesus?
Can you make it?
Similar?
Pass down my card, please.
Exactly.
I don't want to write out.
Make it simpler.
Yeah.
Please.
Pass down my card.
Okay.
Explain what these big words mean.
Let's make something like, let's see here. Let's go x to the second over, okay? I'm trying to explain this as simple as I can. When you look at your polynomial and they're both in order, right? They're in standard form. That means highest degree to lowest degree, okay? If the top one is smaller than the bottom one, then the line y equals 0 will be the asymptote. That means that if I were to graph this is my asymptote. That is my horizontal asymptote. That's only if the numerator degree is smaller than the denominator degree.
So it won't cross X.
So it won't cross X. Okay?
So,
Never mind.
I'm just thinking like if it was like opposite.
We're good? Okay.
Wait, so the numerator is smaller than the
Yeah, if the numerator is smaller than the denominator, then this y equals 0 will be the asymptote. Now let's flip that role, okay? If the top one is bigger, like let's say this is a 3 and that's a 2, then it will not have any horizontal asymptotes. It will not have horizontal asymptotes. If the numerator is bigger than the denominator, then it will not have horizontal asymptotes.
What if they're the same, like both of them?
If they're the same, then you might have oblique asymptotes.
So, oh, okay.
If they are the same, then you will have oblique asymptotes or diagonal asymptotes. So if they are the same, you will have oblique asymptotes.
So when the top is bigger than the bottom, you'll
And they will be at, let me show you an example. So let's say I had for some reason 2x to the third over 3x to the third. Okay? So here, the degrees are the same, right?
yeah.
So obviously that means that I don't have a horizontal, it's not the first one, it's not the last one, it's the same one. I will have a oblique one, a diagonal asymptote. And that will be at the equation y equals 2/3 x. It will be at y equals 2/3 x.
Oh, the vertical line.
Guess where the 2/3 came from?
So 2 and then 3.
The
Wow.
coefficient,
Yeah.
Okay.
The first with the biggest eyelash. The first.
That's if the degrees are the same.
Yeah. Okay. But like if it's like 2x plus, 2x to the third plus x, like would it just be 2/3 because it's the first?
It's
I
just
guess
it's
first
the
value,
leading
just the leading coefficient?
Yeah.
Oh no, I lied. I messed it up.
Liar. What did it
Why is it not y equals 2/3?
It's
That's
sorry,
Reciprocal.
totally lied.
Why? Wait, what?
This is the one that will be oblique. I lied.
What?
Aren't you?
Okay, let me start again because I messed up. Oh my God! My name's Jose, not Jesus. I ain't perfect. Okay, so if the top one is smaller than this one, you're going to get the line y equals 0, right?
Yeah.
That one's okay.
Uh-huh.
If they're equal, let's say this was 2/3, then my asymptote will be at 2/3. So positive 2/3 will go 1, so it'll be there. Okay?
So wherever you're
Yeah, don't listen to this one yet, okay?
So wherever you're leading, whatever your leading coefficients are.
Yeah.
2/3. That's where you're.
Oh.
Yeah, that's why I put 2/3 in there, okay? I want to make sure you're good before I move on.
No,
Go
she's
for it.
not.
So it would just be a horizontal line.
Yes, it would be horizontal. This is my oblique one. Okay?
Ones
If-
are the same, when the degrees are the same.
Yeah.
Isn't that what you already said?
No.
No.
So what's the difference between the first one and that?
Yeah, at first he said when the.
For the first one, your asymptote will be the line y equals 0. It will be this line. Okay? If they're the same, then you want to get these two leading coefficients because that's where we'll be at.
So in a way, it would just kind of like shift that line.
Yeah, it would shift the line. So that would be 2/3. If this is 1, then it would be up here 2/3. If it was, for some reason, I don't know, 5 and 3 here, then I would be up 1 and about 2/3 of the way. And they could be negative as well. Okay? So my bad.
That makes sense.
Now, if the top one is bigger than the other one,
Like.
which is the last one, then you have no horizontals, but you have the obliques or the diagonals. Okay? I apologize. That's my bad. Okay? So if the top one is bigger, you have no horizontals, can have the obliques. This is Pop-Tart's fault.
Okay, that makes sense.
Oh my god.
What's
That's
up?
why you shouldn't eat pop-tarts.
Wait, okay.
No, the degree.
I knew what it was.
The degree. Okay?
So all of this is based off of the degree value?
The degree. All based off of the
What?
degree.
What are you having problems with? So when the top one is smaller than the bottom one, you're gonna have it at 0, line
Yeah.
0. When they're the same, you're gonna get the leading coefficient at the top and the leading coefficient on the bottom, and that's where your
So
y
they're the same degree.
Yeah.
The leading coefficient.
Yeah.
Thanks,
Thanks.
Thomas.
Thomas.
Put those pencil etchers next to the pencil. You can catch it like wall.
Okay, I can move the slide. All right, so look here. Does this have a horizontal asymptote?
Yes.
Actually, let's start with verticals. Are there any vertical asymptotes here?
No.
No.
Yes.
No,
Wait.
stop. Hang
3.
on, hang on, give me a second.
There aren't any, right?
There aren't any.
I was like, you told us if there's like less than, but it's none. So
No, hold on. Say what I said. Say what you think I said.
I thought you said when you have like x squared plus 1 that there aren't any.
Whenever like you have to have a negative to add up to the other values that you
Okay.
can have, but
Yeah.
whenever it's squared.
We'll have to try that out. I don't know if that's exactly what I said, but it works in this case. Okay. No horizontal asymptotes, right? Do I have horizontal? Sorry. We have no vertical asymptotes.
But
Do we have horizontal asymptotes?
Yes, sir.
Where?
It's at
At
3
3.
because 9
It's at 3.
9 squared divided by, or no,
Versus
just
9
the
divided by
leading
3.
coefficient. So it'd be 9 divided by 3.
which is 2.
See it? Cool beans. Thanks, Thomas.
I thought N and M were X.
Yeah,
They are.
they're the same. So
The
we
same
look at the
exponent.
coefficients.
Yeah.
And you divide by 3.
So 9 divided by 3 is
3.
3.
3. Is there anything?
Okay?
No.
I can change it.
Yes. Oh.
We already did that.
Oh.
That is like, is that the mathematical
It's
part of it?
A and
Yeah.
It's A over B.
Yeah, here.
Okay. I think we just did this, didn't we?
Yes.
Okay.
What the?
Mr.
Yes. What the hell? That's the same problem.
Yeah, did I just copy it like 1,000 times?
I don't know. Keep going. Yeah, that one is the same one. That one's the same one. That one's the same one. Oh, yeah, I was having to do that.
No. Look at the powers.
Oh. Ah, powers are different. Thank you. So this one, they're the same. This one, they're not the same. Well, these are just examples, right?
Yeah.
Yeah.
I mean, if we don't want to see them, that's okay.
No, let's keep going.
Is this going to have
0.
vertical asymptotes? Will it have horizontal asymptotes?
Yes.
Where?
Y equals 0.
Y equals 0. So that means that my y-axis. Okay.
No.
The verticals would be at the zeros of the denominator. I try to put a dotted line on top of it, yeah, to serve as my asymptote. Yeah, that's the end of the sentence.
Alright, you're good with this.
I can change it.
Voila.
Where are my horizontal asymptotes?
There are none.
They're oblique.
There are none. So we'll have oblique.
Oh, okay, that's what.
I just don't know how to find the oblique.
You're not gonna like it.
No, I don't think I will, but that's okay because you gotta learn anyway.
Okay.
We really will. Is there gonna be any oblique ones on?
So this This obviously has no vertical asymptotes, no horizontal asymptotes, but we do have, or we could have, the obliques, right? Guess what you have to do?
Quadratic formula.
Yeah, you actually have to divide them. I wonder why we did long division. Oops, wrong way.
Mr. Munoz, I really don't mind that. I think you're wrong.
All right, so anyways, no horizontals on this one, right?
He's about to show us, and he was like,
So, this is just graphing stuff and stuff you should be finding right away anyway. Figure out what type of symmetry it has. If it has x-axis symmetry, or sorry, y-axis symmetry, or if it has origin symmetry. Figure out where the y-intercept is. That should be pretty simple, right? You make x 0, and then find the x-intercepts, which make y 0. Find any vertical asymptotes. Okay, those are the zeros of the blah, 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 blah. See if there's any horizontal asymptotes by looking at those degrees again. Plot a couple of points on each side. That's just primitive stuff, right?
Yeah.
I want to try to get you the other one. Use the information obtained previously. I'll give you some insight. It doesn't always happen, but typically, let's say you did have asymptotes like this. Usually, if you have one part of the function go down towards negative infinity, it will always come back from the other end for some reason. I don't know why. Don't ask me. Maybe it went around the infinity universe and
Wouldn't it?
ended up on the other side.
Because it's on the bottom side of the asymptote on that side, but whenever it gets down to the bottom and it runs closer and closer to the hole, whenever it finally gets there, it doesn't have to come from the top, but it still can't reach 0, and that's why it goes the opposite direction.
But that's the thing; it can never cross this line. So,
Yeah, but like whenever it goes closer and closer to it.
which is really trippy. Let me show you another.
Doesn't it get like
So maybe you have. I should use it on the color, right? Let's say you had a couple of asymptotes. Okay, something like this. Typically, they will do this. Okay.
Yeah.
Now that's not necessarily always 100% true, but most of the time, you can bank on that. All right, moving on. So let's start by graphing this thing. Do I have any vertical asymptotes?
Yes, sir.
Where?
2.
2. 1, 2. Do I have any?
horizontal.
Thank you. Horizontal. It's just so many asymptotes in one lesson.
3.
Where?
3.
Okay. And now to figure out what it's doing, you pick some points. Like,
1.
make
Make him easy.
x 0, right?
Yeah.
If we make x 0, what do we get for y? Negative 3 halves, which is about somewhere in here. Right?
Yeah.
So I'm telling you that it's probably going to do this, and then come back this way like that. And you can test other points if you want as well, to confirm that. Which is what you should do, because you have to do it at Math Lab anyway. But I think you guys know how to do input-output tables, right? Let's not snooze with that. Can I change the slide? Slant asymptotes, obliques. The graph of rational function has a slant asymptote if the degree of the numerator is one more. It is one more than the degree of the denominator. Has to be one more though.
Only one?
Yes.
I wonder if it's more than.
Then you can't, because it would. The deal behind that, let's say we had third degree, right? And we had x degree. You guys remember when we did the division? We always. Well, it's exactly one more, right? But what's going to happen is 2 of these will cancel with that, which will give you a y equals x type of line. And it has to be a line. So if it was more than that, you'd end up with something quadratic. And that's not, I mean, you can have like, I don't know if I've ever seen that business going on. They're always lines for asymptotes. That's why they have to be 1 degree in separation. I know that one. All right? So, 1 degree of separation. Top one must be higher by 1. Like in this case. Okay? So, let's do some sketching. Do I have a vertical?
Yes.
At
2.
2. So 1, 2. Pop, 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 pop. Do I have any horizontals?
Yes, we need to do long division.
Horizontals.
Horizontal.
Do I have horizontal asymptotes?
Yes.
No,
No.
but they're oblique.
Because the numerator is 1 degree more than the other one.
So
So,
we can use synthetic division for that, correct?
yeah, you can do synthetic if you want. So we've got 2, -5, 7. We'd have a 2 here. That's 2, 4, -1, -2. Did that even work?
No.
No. Because you.
That would give me 5. So, here's what I want to get out of there. It should be that piece. Y equals 2x minus 1. I'm going to verify that real quick. Oh, it's at the end. Yay! Yep, there it is. Okay? So you graph this line, there's your,
We can kind of ignore the remainder
Uh-huh.
in this case.
yeah. Yeah, but that's the equation of the line to the oblique asymptote.
Okay.
I think that makes us done.